So the first thing I want to go through is what the difference is between a scalar quantity and a vector quantity. Both are measures of things. So a scalar just measures the amount of something. Okay. So any standard thing that you measure, it would be a scalar because you're measuring the amount of it, or the fancy word is the magnitude of it.
Okay, yeah.
And a vector quantity is a bit different because it measures magnitude and direction. So it's something where we would say it has this amount in this direction. So as an example, a scalar would be mass or energy, but also speed and distance. But a vector would be weight, force, velocity, displacement. So the velocity and displacement bit I'll go through in more detail, but just quickly, your mass is just the amount of matter you have, and that doesn't depend on which, it's not pointing in any direction, it's just your mass. And an energy of like a kettle, it's not going in any direction, it's just, it's energy store, okay?
What is mass measured in again?
Kilograms.
Right.
I'll go through that
And
as
then
well.
weight is measured in newtons.
Yeah. So speed and velocity are the same thing, but velocity has direction. Distance and displacement are the same thing, but displacement has a direction. So velocity is speed with a direction. I'll give you an example to understand that better. If I'm traveling from A to B and I'm going on a run, so I don't care about just getting there as fast as possible. I just want to go on a nice fun run around the park. So I go this way, this way, this way, this way. The overall distance I've traveled is that whole curve that I've drawn. So it might be like 400 meters. But if the distance, the shortest distance from A to B is 100 meters, then my 100 meters would be my displacement.
Yeah.
It's how much I've displaced by from my start to my finish
That I remember.
in that direction. Whereas my 400 meters is my distance traveled. Okay, because remember, displacement is only how far you moved in that particular direction. Okay, so then if I move back over here, then from here till here, I've just traveled 70 meters. I've displaced myself by 70 meters from my starting point in that direction because I've moved back by 30, but my distance would have been 130. Cool. So now that we understand the difference between scalar and vector, let's look at some graphs. So if we have a distance time or a velocity time graph, the interpretations are different. So the first part of the distance time graph, what would that be showing?
So one is a steady increase
In what?
in distance
Which
traveled.
is? So how would you interpret that in terms of somebody's movement or a car's movement? If somebody's going on a run, what are they doing when it's at one?
They're running at a
Moving.
constant speed.
Exactly, moving at a constant speed. What about at two?
2 is stationary.
Exactly. So they're not changing distance, so they're not moving, so they're stationary. And 3 is moving again, but the speed is increasing.
Yeah, so it's accelerated.
It's an acceleration. Exactly. But what about one on the velocity time graph?
So one, their speed is steadily increasing and
So what's the word if your speed is steadily increasing?
they're at constant speed.
They're at a constant acceleration.
Constant acceleration, yeah.
Because their speed is increasing. So they can't be at a constant speed. Their speed is increasing,
And
which
then
is
2 is a constant speed.
exactly, which is different from number 2 in this first graph, where a flat line meant it's stationary.
And then 3 is constant deceleration.
Good. You can also use the word velocity for number 2, but it's fine.
Okay.
And number 4
And then
is
4 is the same as 2.
4 is stationary because it's
Oh,
flat,
yeah.
but it's at 0.
Okay, yeah, yeah.
So if you're moving at 0 meters per second speed, you're not moving. And then 5 is
5 is
because velocity is a vector, so it takes into account direction.
oh, so
So
5
it's actually accelerating
in the opposite direction.
backwards. So it could be reversing, or it could have changed direction, turned around, and started to accelerate backwards. But because velocity is a vector, it factors that into it. So minus 20 meters per second and 20 meters per second are the same thing in opposite directions.
Right. So what would it mean if on distance time graph it was like that? And
Distance isn't a vector, so it wouldn't
it'd
mean
just be like
it
a
wouldn't happen.
constant
It's not
speed.
possible.
Oh, right.
You can't decrease your distance. But if it's a displacement, then yeah, it would be the same thing. You're going backwards.
Right, okay.
If it was displacement, but they won't ask you that. Okay. With each of these graphs, we need to know what the gradient and what the area tell you. Any ideas?
Does it tell you about the grid as a gradient tell for the distance, the gradient tells you does it tell you your speed?
Yeah. However steep it is, it tells you the speed.
Yeah.
And the area doesn't tell you anything in this one. What about the gradient in a velocity time graph?
It tells you the movement of your speed.
Acceleration.
Oh, right.
Yeah, exactly. The movement of your speed, the change of your speed,
Yeah.
which is acceleration.
Cool.
And the area under the graph would tell you your distance traveled. So what are the equations for these things? So first of all, gradient is worked out by doing change in y divided by change in x after you pick 2 coordinates.
Is that the same as rise over run?
Yeah, rise over run. And based on that also, average speed equals distance traveled divided by time taken. So speed equals distance divided by time, if it's average speed. And acceleration.
Change in velocity over time.
Exactly, change in velocity over time taken. Good. Distance is in meters. Time is in seconds. Acceleration, speed is in meters per second.
Acceleration is meters per second squared.
Exactly, because meters per second, so meters per second squared. And out of these, acceleration and velocity are vectors. Speed, distance, and time are scalars. So these are Newton's laws. The first law just tells you what happens if there is no resultant force. So first of all, what is resultant force? If I have an object and it's pushing with 8 newtons to the right, but there is a resistance of 3 newtons to the left, the resultant force is 5 newtons to the right. Okay. So if there was no resultant force, so if it was 8 and 8, so 0, then the object would be stationary, which sounds obvious, but it's important to remember. Or it could also continue at a constant speed. Okay, so an object can easily move if there's no resultant force, but it would just continue to move at the same speed which it was previously at. If there is a resultant force, the object would accelerate or decelerate. But that's really important. You can't say, you'll get it wrong if you say, if there's a resultant force, the object will move, because it won't move, it will accelerate or decelerate. Okay, it will change its speed. Okay.
So would you have to say if there is a resultant force, it accelerates or decelerates?
Yeah,
Just
but
say-
it will tell you like which way it's going and stuff. So you
Okay.
could probably just say accelerate or decelerate, whichever one you need to.
So you
So
don't
that's fine.
necessarily have to say both.
Yeah. The second rule is, as you said, the equation F equals ma. Okay. Mass is measured in kilograms and A is measured in meters per second squared. Force is measured in newtons. Okay. And then that leads us to another equation. Weight equals mass times G. Mass is still in kilograms. G is the acceleration on Earth, so 9.8 meters per second squared, for example. And weight is a type of force. That's really important. You can remember how to not mix up weight and mass by remembering that weight is a type of force. But there's loads of different types of force, like driving force, air resistance, friction, and weight is just another type. Mass is the same wherever you go. It's your amount of matter. In everyday life, we use weight and mass interchangeably, but in physics, they're different. So when we say we weigh 60 kilograms, we have a mass of 60 kilograms.
Right.
And on the moon, we'd still have a mass of 60 kilograms, but our weight on the moon would be different because acceleration, gravity on the moon is different.
Yeah.
So we'd apply a different force onto the moon. And then the third rule is just that when two objects interact, they exert equal and opposite forces on each other. So an example of that is if I have something on a table which has a weight of 100 newtons, the table doesn't collapse. So if the table wasn't collapsing, then surely the weight can't be 100 newtons. I mean, the resultant force could not be 100 newtons because if it was, the object would accelerate based on the first law. So surely the table is exerting a force of 100 newtons upwards so that everything is stationary. Okay. So here's an example where we apply all three of or especially rule one. Okay. So when an object reaches terminal velocity, and they could ask that about a race car, a rocket, or a skydiver. So let's just say a skydiver. So a skydiver, terminal velocity is its highest speed. So we're seeing how an object can get to its highest speed. So a skydiver will first accelerate because its weight is bigger than air resistance. Okay. Then, as the skydiver falls, it eventually reaches a constant speed, y. So does weight ever change? Like when you're falling?
No.
No, weight won't change, right? So weight will stay the same, but you'll hit the air faster. So air resistance will increase. Okay. So eventually, if weight's not changing and air resistance is increasing, then weight will equal air resistance. Okay. And if that's the case, then because there's no resultant force, the skydiver will have a constant speed. That's quite a common 4 markers for most examples. Okay, but you're just applying the first rule of like Newton's first law. So you're saying it will accelerate when one force is bigger than the other. Over time, the forces equal out because one of them is not changing. And then when they are equal, the object will go at a constant speed. I could easily apply that to a race car and say the engine force will be very big and higher than drag or air resistance or friction. Over time, the maximum engine force will stay the same, but the air resistance will increase. And eventually, when the engine force and the air resistance are equal, the rocket or the car will move at a constant speed. Well, so a specific car or a specific skydiver will have its terminal velocity set. But if you wanted a different car with a different terminal velocity, you could give it a bigger engine force, or you could change its shape so that it has less air resistance, or change its tires so it has less friction. So one example of a force which we applied was weight. There's one other type of force that we should know about. So it's just F equals KE, which is the force on a elastic object is equal to the spring constant times extension. It basically says the amount a spring extends by is directly proportional to the force applied, or like the weight applied or something, until its limit of proportionality. So that's Hooke's law, if you've heard of that. Okay. There's like a
Oh, yeah,
practical
heard
where
of that.
if I double the force, the spring's extension will double. If I triple the force, the extension will triple. We were doing
Oh,
direct
yeah, that's like
proportion
yeah,
we were doing direct proportion in maths,
Mm.
and K is the same thing.
right.
But this is until the limit of proportionality. That was the criticism of Hooke's law, that it's true, but then after a certain point, let's say you times 100 the force, the extension won't times 100, the spring will break.
Yeah.
Okay, so force is directly proportional to extension until the limit of proportionality. That's it. And there's a practical behind that as well.
Yeah, I remember we did that. We had to put different weights
Yeah,
on
you put
bottom of
weight
the
one by
spring.
one and you see how much it
Yeah,
is.
how much is it
Cool.
bring to?
An extension is just the new length minus the old length. The next,
They're on the stairs, I think.
so the next thing was momentum, which is mass times velocity. So a heavier object at the same speed will have more momentum, and a faster object at the same mass will have more momentum. And then that itself is too easy, but what they'll do is they'll combine this with your understanding or application of the law of conservation of momentum.
Mm.
Do you know what that is?
I can't remember.
Total momentum before a collision or an event equals total momentum after. Okay.
Right.
The key thing, so momentum is mass times velocity, but let's say two cars crash into each other. Let's say one car is still and another car crashes into the back of it. The car which is still is going to gain momentum because it's going to be pushed forward, and the car that crashed into it is going to be put to a stop. So that's surely going to go down in momentum. So momentum before does not equal momentum after. The key is that total momentum before equals total momentum after. Okay, so both the momentum of both cars added up before will add up to both the momentum of both cars added up after in a closed system. Okay. So it would be too easy to calculate the momentum of the skateboarder after. So they're asking you to do like 3 or 4 things in one go. So the skateboard and the skateboarder are not moving at all before. So momentum of skateboarder before is 42 times 0, which is 0. And then the skateboard before is 1.8 times 0, which is 0. When you add them up, you get 0. Now we do it for after, okay? You won't get much harder than this, but this is like what it should be, apart from the really easy ones. So the skateboarder jumps forward at a velocity of 0.3. So it would have a momentum of 42 times 0.3. Okay. So 42 times 0.3 is 12.6.
Is it not the same as before and after though?
No, that's the thing. The skateboard can change. Remember when I said like a car can crash into it? So that would never make sense. How can your momentum always be the same? The key is the momentum of them added up is the same.
Right, okay.
So now the skateboard after, this is where the question gets really started. So we're going to do the skateboard after, which is 1.8 times question mark. And we have no idea what that is. But we know that they have to add up to 0. So it has to add up to minus 12.6 in order for momentum to be conserved, right?
So it has to be negative 0. Oh no.
So we do 1.8 x equals minus 12.6. So x equals minus 12.6 divided by 1.8, right?
Yeah.
So 12.6 divided by 1.8. So minus 7 meters per second. It says velocity as well, so you have to put a minus.
Right.
So because it's going 7 backwards, the momentum of them both added up is 12.6 and minus 12.6, which makes 0. So total momentum is conserved.
Right.
So in the harder ones, you wouldn't just use momentum as mass times velocity. You'd use momentum equals mass times velocity and the law of conservation of momentum.
Right.
The last thing is just stopping distance, but I'll give you a way to remember how to define it. There's no set definition for stopping distance itself, so we just say that stopping distance is thinking distance plus braking distance. But we can define those two. Okay. So braking distance is the distance after touching the brakes until you stop. But don't say the time after touching the brake until the time you stop. That wouldn't make sense. It's the distance. Okay. And thinking distance is the distance after the distance traveled whilst you decide you want to stop, or decide you need to stop, or think to stop until you first touch the brakes. Okay. So think to stop, touch the brake, and then touch the brake until you stop. Those are the two parts of stopping distance. And stopping distance itself doesn't have any factors, but thinking distance and braking distance has a bunch of factors. So braking distance is the quality of tires, wet or icy roads or slippery roads,
And
the quality of your brakes.
brakes, yeah.
Exactly, yeah. And one other hard one, which I'll come back to. And thinking distance is if you're tired or sleepy, drugs or alcohol, distractions like music or like phones. Like in the CGP book, I always see a picture of a guy driving and there's like a sheep in there on the road.
Oh.
And it's like a distraction. That helps you remember it. But yeah. And then the last one for both of them is a bit weird. It's actually speed.
Yeah.
So speed won't affect your reaction time, but if your reaction time is 0.3 seconds, okay, at 100 miles per hour, or 0.3 seconds at 40 miles per hour, your distance will then change. Okay. So if it says reaction time, you can't say speed.
Yeah.
But if it says braking distance, it's going to be multiplied by your speed anyway.
But then if